Hello, this is Judah Levine. I'd like to tell you a little bit about the techniques for constructing clock ensembles and timescales. I'm going to talk about the principles of these algorithms, but I'm not going to talk about the details of the algebra, which are quite complicated. I have some references at the end, which you could look at if you want to see some more details about the actual algebra. Now, the idea of an ensemble is to combine the data from clocks, from a bunch of local clocks, to generate a local copy of the remote reference. The remote reference could be, for example, a signal from a GNSS satellite, or from UTC, or from UTC of a lab. The source of the reference doesn't really matter for the technique. But before you start doing it, you have to decide, do we want to maximize the time accuracy of the local copy with respect to the remote reference? Or do we want to maximize the frequency stability of the local copy with respect to the remote reference? The reason that decision is important is that those two requirements, in some sense, are incompatible with each other. And so you have to kind of choose either one or the other, or some combination of the two. And typically making one better makes the other one worse. Finally, if there is a significant cost in acquiring the data, for example, if you have to use a lot of computer cycles or a lot of memory to acquire the reference data, then that is another consideration that you have to take into account in deciding how to run the algorithm. Now, one of the issues is, why are we doing all of this? What's the point? And there are a number of advantages. First of all, the local copy is potentially more reliable than the remote link. It's not affected by a failure of the remote link. The ensemble can detect clock failures, and as you'll see, local copy can attenuate link noise, which is really quite important if the data come from a GNSS receiver, because those data typically have a lot of noise at short term. The statistics of the local clock can detect spoofing attacks. Basically, you have some idea of what the time is just on the basis of the local clock data, and you can detect if the difference with respect to the remote clock is not at all what you expect. Finally, there are situations in which the remote reference is not always available. For example, that's true for UTC, where you can't always get the data. And what that means is that the local clock is running in holdover most of the time. It remembers the calibration and then has to run in holdover between calibrations. And when that's the situation, then the holdover characteristics of the clock, the stability of the local clock between calibrations, becomes very important. Now, before we begin to discuss the ensemble, I should discuss a little bit about how a clock is constructed. The basic thing of a clock, the basic clock has two parts. One of them is an oscillator, which generates periodic ticks, periodic interrupts of some sort. If it's an electrical oscillator, then it might be that it generates a tick each time the voltage output goes through zero with a positive slope. That's just one way of doing it. The point is that the ticks are equally spaced and are periodic based on the electrical frequency or the mechanical frequency of the reference oscillator. And those ticks are then counted by some device, which is also part of the clock, and the time is simply the count of the ticks. Now, the clock, the time of the ticks is accumulated typically in units of seconds, where a second is defined based on whatever the period of the oscillator is. For example, if it's a cesium oscillator, then the cesium frequency is 9 gigahertz about. So you count 9 billion cycles, and that's 1 second. If it's some other oscillator, then you count that appropriate number of cycles to get a second. You then combine the seconds to get a day, where there are 86,400 seconds in a day. And the days are simply counted. The counting is typically done with modified Julian day number, which is simply a count of days from some remote origin. The point of the remote origin is that it's sufficiently far in the past so that all the times that are of interest are positive quantities. Now, the time difference, xij, is the difference between two devices measured at the time of some reference time. That is, tk is a reference time from some external oscillator, and when tk rings the bell, you look at the difference in the time between device I and device j, and you take the difference, and that's xij. If you have a thing like a time interval counter, which is a typical way of doing it, then the counter measures the difference modulo the period. For example, if the ticks happen once a second, then the time interval counter is measuring the time difference modulo 1 second. The convention is that if the time difference is positive, then device clock I is fast, which means that the time, a time occurs in clock I earlier, before it occurs in clock j. Now, there are two more quantities which are used to characterize the clock. One of them is the frequency of the clock, which is simply the evolution of the time difference between successive observation times, tk minus 1 and tk. Now notice that this frequency is the evolution of the time difference. It is not the same thing as the frequency of the electrical oscillator that we talked about several slides ago. It is simply time evolution, as I show on the slide here, and that is roughly speaking the difference in the frequencies, which is roughly speaking the fractional frequency offset, because the frequencies are usually quite similar, so that the difference is small, and approximately it's just the fractional frequency difference between the two devices. Frequency is the division, the ratio of quantities with the same units, that is a time, the numerator and a time in the denominator, so the frequency has no units. It is a dimensionless quantity. The drift term is the evolution of the frequency, and it's defined the same way. It's the difference in frequency between the previous time measurement, tk minus 1, and the current one, tk, divided by the elapsed time. Since the numerator is now dimensionless, the denominator has units of seconds. The units of drift are 1 over seconds. Now, in principle, the frequency and the frequency drift defined this way are observable quantities. You could actually measure them, but it's typically not done that way. It's more usual to measure the time differences and to then compute the frequency and the frequency drift from the time data. So that although the frequency and the frequency drift are observable in principle, they're usually not observed in practice. Now, real-world clocks have oscillators that have systematic offsets from the standard frequency. The systematic offsets might come from electromagnetic fields that affect the energy levels of the atoms, if this is an atomic clock, or from temperature effects, if it's a pendulum clock. There are, if the atoms are in a cell, as they would be for a rubidium device or a hydrogen device, then there are collisions between the atoms and the walls of the cell. And in a beam device, there could be collisions between the atoms and the other atoms. And all of these things affect the frequency of the device, that is, affect the physical frequency of the device. There are also electrical effects from the electronics that locks the oscillator to the frequency of the atoms. And these two effects, these two sources, have a systematic offset, which means devices that are nominally the same have different offset frequencies, but it also has a stochastic effect, in which case the frequency is varying because the driving effects vary slowly in time. Now, because time is the integral of the frequency, although the frequency may have a random quality, the time is the integral, and therefore the time typically has a random walk character, because the integral of the frequency of a random frequency is a random walk. Now, using these ideas, you can construct a model of a clock, which I show here, and with a model of a clock essentially predicts the time, frequency, and frequency drift at the current measurement point, tk, based on the values at the previous measurement point, tk minus 1. And it uses the terms that I've described in previous slides, the deterministic offsets and the noise terms. usual arrangement with cesium clocks, with most other clocks, is that the drift term is small. In other words, the contribution of the drift term to the frequency change in the Y estimator is small compared to the frequency noise. And what that means is that the time between measurements is small, as given on that last line, so that the evolution of the frequency is predominantly driven by noise rather than by the deterministic offset of the frequency due to drift. By the same token, the frequency drift itself, changes very slowly, so that the drift between the previous interval, the d at tk minus 1 and d at tk, are differ by a small quantity, so the drift is essentially constant over time. It changes, but it changes very, very slowly. That's one assumption. And the second assumption is that at any time, the contribution of the drift is small compared to the contribution of the frequency noise. Now, that has good news and bad news. The good news is that the drift can be ignored in first order because it's a small effect in one or two time series. But the bad news is that it's hard to determine the drift, because it's hard to distinguish the drift from the noise of the frequency devices without integrating for a long time. And that's an awkward arrangement. It means that the drift, in almost all time scales, the drift is a hard parameter to determine. Now, there's also noise in the measurement process. And the noise in the measurement process, unlike the noises in the previous slide, which are part of the evolution, that is, the value of the state at current time is the value of the previous time plus a noise. So the noise is integrated by the evolution equations. The measurement intervals the noise in the measurement is uncorrelated, so that the noise at each measurement is simply has a mean of 0, so that the measurements don't have any systematic offset, but they're noisy. They have fluctuations with known variance. Now, what that means is that the noise in the measurement process is a white phase noise. It affects each one of the measurements in a way independent from the previous measurements. But the other noise processes, because they're in integrals, they are effectively, if they're white noises, they integrate to random walks, so that the three effects, the noise in the three terms, because they're in the evolutionary equations, they introduce a random walk in phase, a random walk in frequency, and a random walk in rate. In each one of the cases, these noise terms have a mean of 0. They have known variance, but again, the effect on the time and on the frequency and on the drift is not the parameter itself, but it's integral. And that means that the integration tends to turn them into random walks. Now let's turn to a few examples. The first example is the simplest one, in which I have one clock 1, and I'm going to steer it to some reference. So I measure the difference between clock 1 and its reference time, and I get x1r plus epsilon. That is, I measure the difference in time plus noise. I feed that difference into what I expected. I take the difference between the measurement noise plus noise that I got and what I expected, and that difference is used to generate a steering correction. I apply the steering correction to the hardware, maybe to the clock itself, but more usually to some external device outside of the clock. So the clock itself is not adjusted. It's just the external device is what's adjusted. And maybe I update the model, and I'm going to talk about how you update the model, but that's really where all the algebra comes and all the difficulties are, because it turns out that's going to be an ambiguous business. Now, this is a simple model. It provides some holdover. The clock will continue to provide some time based on the last steering if the reference fails, or if the link to the reference fails. On the other hand, it has poor error and spoofing detection, because when the data don't agree with what you expected, you don't quite know what to do with it. You don't know whose fault it is, whether that's the local reference, whether it's a difference, whether it's the local clock, and so it's hard to use this to detect errors in the clock or in the reference or in anything. It has a single point of failure, of course. If the clock dies, the clock dies. That's the end of it. On the other hand, it's better than nothing. It clearly provides some amount of attenuation of the noise in the link, and has some amount of error detection, but not a lot. Okay, so let's fix the problem by having two clocks. And I show you the picture here. The clocks are the same. Each one of them has a measurement with respect to the remote reference. In each case, I take the difference between the measurement x1r or x2r, and of course the measurement noise. I compare it against the model that I developed for that clock. I take the difference between what I measured and what I expected, and I use that to steer the steering hardware. So it's the same as the previous method, except here I have two devices. And of course I could have 3 devices or 4 devices or 5 devices. I can duplicate this as much as you like, and each one of them produces an independent output of the difference between steered to the difference between the local clock and the reference. Now, each clock is independently steered to the reference time, and so the measurement noise affects both channels. To the extent that the measurement noise is not correlated, which is the usual case, the two channels are affected differently. It detects uncorrelated errors, and it detects some spoofing effects, but not all of them. It certainly has better holdover than method 1. On the other hand, uncorrelated noise can introduce a random walk between the channel times, and that's usually what happens. The noise in the measurement process and the noise in the link is uncorrelated, and it gets integrated up by the process of taking the difference between what I expected and what I got and applying it to the steering correction, and therefore the steering correction is the integral of all the various errors, so that a white noise in the measurement process gets integrated up into a random walk. And the result of that is that the difference between the two devices tends to walk away, and they tend to walk away from each other, and that's a problem in the long term. So I have to deal with that by going back and getting correction data. So it has only limited holdover capability because it's in the longer term it's going to have a walk-off. Now I can combine the outputs. If I think the difference is purely noise, then I can combine the outputs. And the usual way of combining the outputs is to take the weighted sum of the two values, where the weights are determined by the prediction errors. So that I say that a clock which had a small prediction error, a small delta, was able to predict the difference very well, and therefore it's a trustworthy clock. It should get more weight. And the usual statistical weighted average is shown on this slide, where the output is the weighted sum of the two outputs, assuming, of course, that the differences are only noise. If the differences are systematic, then, of course, the weighting average doesn't produce a more reasonable value. It simply averages the systematic value, and it's not the mean of it is not 0. The variance of the weighted average is better than the variance of either clock. That's just the usual characteristic of an average. It tends to attenuate the noise in the process, and so that as you can see on the slide here. Now, the idea of the ensemble method is basically based on the method that I showed in the previous slide, except that instead of having each clock measure the difference between its time and the time of the remote reference, which doesn't scale very well. It requires that I have this remote reference link over and over and over again, one for each clock. What I'm going to do here is I'm going to have one clock, which is linked to the reference device, and I call that clock 1, but it really doesn't matter. It's one of the clocks, and I measure the time differences locally between clock 1 and all the other clocks, so that I have local measurement of time until count or whatever that measures the local difference between the reference clock and all the other clocks. And now I initialize clock 1, I initialize the model of clock 1, so that its corrected time, that is its time corrected by the model, reproduces the reference. So clock 1 represents my initial value of the reference as best as I know it, and I assign that to be the ensemble time. So the ensemble time is simply my estimate of the reference time at the initialization time. I do that as best as I can, and I set the ensemble time equal to the time of the reference clock corrected by its model. Now I then initialize all the other clocks so that the corrected clock model for each clock compared to clock 1 agrees with the measured time difference with respect to clock 1. So that I measure clock 2 against clock 1, and I adjust the model of clock 2 so that the model of clock 2, the corrected time of clock 2, matches the measured time of clock 2 minus clock 1. And for clock 3, I do the same thing. I adjust the model of clock 3 so that the model of the corrected clock 3 agrees with the time difference between clock 3 and clock 1, and so on and so on. And then if you do a little bit of algebra, what you can show is that each one of the clocks represents another estimate of the ensemble, in which I estimate the ensemble as the model time offset with respect to clock 1 plus the measured time offset with respect to clock 1, and it's just the ensemble average of each one of the clocks. You might think of each one of the clocks as providing an independent helping estimate of what the ensemble time is. Okay, now at the next time step, I do the same thing. I have each clock, I measure again the time difference, and I continue the model, extrapolate the model forward, and what I get is I wind up with, if I have n clocks, I wind up with n independent estimates of the ensemble time, which is n independent estimates of the local version of the remote reference. So the ensemble time reproduces the remote reference as best as I can remember it from the initial version, and it does that by taking the average of all the clock memories of the initial ensemble time. And so basically I used each one of the clocks to try and maintain a memory of what the initial calibration factor was. And so the average, the intent is that the average attenuates the noise fluctuations of the clock and results in a better memory of the initial calibration than I would get otherwise. So that's the intent. Okay, so the ensemble time is the weighted average of the estimate of all the clocks, and of course no physical clock realizes this average, so that I wind up with a ensemble time which is a paper clock. If I need a physical tick, I have to take that ensemble time and apply it to some physical clock. Now, the question of how I combine the clocks to produce a weighting average, well, there are a lot of different algorithms. A common algorithm is to say that a predictable clock is a good clock, so that I weight the clocks that contribute to the average by how well they predict the ensemble average. It's basically the idea that I showed you with respect to the 2-clock model. That is, the weight of a clock is simply how well it predicts the ensemble average. So that is a way to do it. But there are other methods. I can use the a priori noise estimates. There's a whole bunch of different algebraic methods. But the basic idea is I wind up with a weighted average, which reproduces the remote reference in the ensemble time as best as I can remember it. Okay, and now the trouble is, or the difficulty is, that the calculation of the weights is circular, because in each case I look at the prediction of a clock by comparing what it predicts the ensemble time is going to be relative to the ensemble, and of course it was a member of the ensemble, so it appears on both sides of that averaging. Namely, in some sense, it's an average of itself against itself. And what that means is that the prediction error is systematically too small, because a clock is predicted against an ensemble in which it was a member, it was a contributor. If the prediction error is too small, the weights are systematically too large. And I have to be very careful, because if I don't pay attention, a clock that gets a little bit better on one cycle becomes a little bit more better on the next cycle, and a little bit better, more better on the next one, and so on, and eventually takes over the whole ensemble. So I have to limit the weights of the clocks. And in the NIST 81 algorithm, I limit the weights of the clock to 30%, and that's an administrative decision, and it's typical. I mean, it's not unique to NIST. Every timescale algorithm has some kind of weighting limit that weights the limit of the weight, sets a maximum weight for a good clock. Now, of course, if you set a maximum weight for a good clock, because the weights sum to 100%, if you limit the weight of a good clock, you implicitly assign part of the weight to a less good clock. And that means that the bad clocks, or poorer clocks, have more weight than they really should. And another way of saying that is that the ensemble is less stable than it would have been if you hadn't imposed a weight limit. And that's done to keep one clock from taking over the ensemble, but there's a price. And the price is that the ensemble has too much weight to poor clocks, and so it's never quite as good as it would have been if you had not done that. Now, the question of how you update the clock models is complicated. There's a lot of algebraic stuff about that, because I make time difference measurements between what I expected and what I find, and what I measure, but I have to assign that time difference to 6 parameters. There are 3 deterministic parameters, the time, the frequency, and the frequency drift, and 3 noise terms. So I have six places to put that noise, and I don't know where to put it. There's no unique way of deciding where to put it, and so the different algorithms have different models of where to put it. On the other hand, because the algorithm is based on time differences, the overall time and frequency are free parameters. They were set initially based on my memory of the reference, of the local remote reference, but in fact I could have added a constant to each one of the clocks, and that would have changed the models by all of the clocks by the same value, and it would have made no difference to the differences. So that there's an ambiguity in the overall time and frequency of the clocks, which can be basically absorbed in all the models. The ensemble attenuates the frequency noise of the clock because it deals with the average, and that means it improves the frequency stability. On the other hand, there is residual frequency noise, and the frequency noise may be white frequency noise, it may be worse than white frequency noise, and that gets integrated up by the ensemble time algorithms, which means that the ensemble is likely to have a random walk in time, or maybe even worse than a random walk in time. But the ensemble left to its own will gradually walk away from the truth by integrating up the residual frequency noise, so that ensembles, you can't start an ensemble and walk away from it, and that's true for pretty much every ensemble. So let me summarize. The ensemble remembers the initial calibration as best as it can, subject to clock noise. The ensemble detects outliers because I have a whole bunch of clocks which are providing estimates of the ensemble, and I can decide if one of them disagrees with all of the others, so I have a mechanism, there's a machinery I can build into the ensemble for detecting outliers. It has no single point of failure. I have n estimates of the clock of the ensemble, and if one of them fails, well, I have n-1 estimates, so it doesn't make much difference. The ensemble attenuates the noise of the measurement of the member clocks because it produces an average, which if it's done, if it's really frequency noise, well, then it's the average of all the frequency noise or the average of all the drift terms. On the other hand, the clock model integrates residual noise, and what that means is that the system is going to have a long-term stability or long-term instability that's difficult to deal with. And because of the way the ensemble is, the drift terms, which are hard to detect in short term, often become a problem in the longer term. So they have to be dealt with as well, so that the long-term stability of the ensemble tends to walk away from the truth. Here I have some references which will give you some more information on the algebraic equations. Thanks very much.